Is 5 a polynomial? Yes? No. It is a polynomial. It's a degree 0 polynomial. Which, I mean, if you forget that constants are polynomials, that's okay-ish, except it'll screw up what a rational function is. So that is, in fact, it's degree 0. What about 1 over x? Is that a polynomial? Yes? No. Okay, yeah, it's not a polynomial. Polynomials aren't allowed to have x's and denominators. The next one, is it a polynomial? Yeah. What power is that polynomial? What degree is that polynomial? 5. Degree 5. The next one. It's not. Again, there's stuff involving x's in the denominator, so it can't be a polynomial. And that last one again, yeah, that is a polynomial. It's degree 3. Now, these things that I said are not polynomials, they're still like built out of polynomials. Right? They're just a polynomial divided by a polynomial. So probably if we understand polynomials, we can understand polynomials divided by polynomials. That's what today is about introducing. A rational function is a ratio of polynomials. Anything of the form p of x divided by q of x, where p and q are polynomials, is a rational function. They're called rational functions for the same reason that rational numbers are called rational numbers. They're ratios. That makes sense? And let's just, again, just quick definitions check. First one. Is it a polynomial? No. Is it a rational function? Yeah. I see a polynomial in the numerator, a polynomial in the denominator. That's a rational function. Is that a rational function? Folks say yes? Anyone want to know? Good, right? Because 1 is a polynomial. It's a degree 0 polynomial. That's why it's important that degree 0 polynomials are still called polynomials. Otherwise, you would have to fudge around your definition of rational function. X plus x inverse. Think about that for a second. Is it a rational function? Folks for yes, it is a rational function. Anyone for it is not. So let's massage it a little bit. So x inverse, that's like the same thing as 1 over x. And that's kind of like a sum of two fractions, right? That's x divided by 1 plus 1 divided by x. What do you need to do to, so that's like two different fractions that I'm adding together. So I need to get a common denominator to add them. What's the common denominator between those two? So the first bit, I'll multiply by x over x. I guess that would make it x squared over x plus 1 over x. Now is that a ratio of two polynomials? Yeah, so it's a rational function. So the point is, even if it doesn't look like a rational function already, it might secretly be a rational function. Any sum of a couple of rational functions is a rational function. Although maybe that's a bit of a spoiler for this problem. So that function, is it a rational function? Folks for yes? Anyone for no? Good. There wasn't very many hands that went up at all. It is a rational function, and I won't go through doing it. But do you think, well, I'll go through some of it maybe. So you could rewrite that just a little bit as x plus 5 divided by x cubed minus 1 plus x times x cubed plus minus 1 times x plus 1 divided by x plus 1. Does it look like between those two, I'm not going to actually do it, but could I get a common denominator between those two ratios? And once you got that common denominator, you could add easily. The denominator would just be the, I guess, product of those two denominators. The numerator would be something more complicated. But if you were to imagine doing that, would you still get a rational function? Yeah. So in fact, any sum product, subtraction, or division of rational functions is still rational. So even things that might look pretty complicated, as long as it's just like the variable x and some algebra, plus, minus, multiply, divide, it's a rational function. Next one, x cubed plus x plus 1. Is that a rational function? Let's see, folks for yes? Folks for no? So what if I rewrite it just a little bit? Is that the same as this? Is the thing in the numerator a polynomial? Is the thing in the denominator a polynomial? Yeah, it's a degree 0 polynomial, but it's a polynomial. So let's ask that question again. Is that a rational function? Folks for yes? Anyone still for no? Okay, well, but it is, right? There's a polynomial on top, polynomial on bottom. It might be silly to say, well, no, that's a polynomial. You shouldn't think of it as a rational function. And indeed, you shouldn't think of that as a rational function. You should think of it as a polynomial. But every polynomial is a rational function. So when you're studying rational functions, you're also studying polynomials. Any questions so far? All right, the next one, square root function. Is that a rational function? Folks for yes? Anyone for no? Indeed, it is not. But you would write that as like x to the 1/2. And you should maybe think of that as being not rational in the same way as like the square root of 2 is not a rational number. Though we'll see on the bottom of this page why that thing cannot be a rational function. Because we're going to compute the domains of rational functions. And just really quickly absorb, what's the domain? What things are not in the domain of square root? Negative things are not in the domain. So I just point to this. Negative numbers are not in the domain. Just hold on to that for a second. So let's think about rational functions. The same as you would simplify rational numbers, you should always simplify your rational functions. Is there something that cancels in that ratio? Yeah, dx minus 2. So if you can ever find common factors in the numerator and denominator, you should cancel them. And that's important. Whenever I do anything today with a rational function, I'll assume that that rational function is in reduced terms, that the numerator and denominator don't have any common factors. So we've seen 1 over x before, and there is the graph of 1 over x. What is not in its domain? What thing can you not divide by? 0. 0. The only thing not in the domain is 0. No, maybe this isn't the answer to the question. 0 is not in the domain. On the other hand, if I give you a polynomial, any polynomial, what's the domain of that polynomial? So a polynomial is just a sum of a bunch of constants multiplied by powers of x. Is there any number that you cannot raise to a power? So there's no problem there. Is there any bunch of numbers that you can't multiply together and then add? No, you can always multiply numbers together and add them up. Polynomials have domain equal to all real numbers. So one difference between this and the graph of a polynomial, domain of a polynomial is all real numbers. Domain of 1 over x is equal to all real numbers but 0. I don't know, let's just see if you have any other thoughts. So that's like a really descriptive way of saying that's not a polynomial. what are some other differences between this and the way you would expect the graph of the polynomial to look? Yeah.
It has an asymptote.
Yeah, it has an asymptote, both a vertical one and a horizontal. So, for those of you not in the know, the word asymptote will be defined on the next page. So it gets close to this vertical line. And it also gets close to a horizontal line. And polynomials just don't do that, right? If you draw a vertical line, the polynomial will crash right through that vertical line. It won't shoot off to plus infinity near that line. And as for horizontal asymptotes, if I give you a degree 10 polynomial, then asymptotically, for really, really big values of x, the polynomial should just look like a constant times x to the 10, not like 0. So this is definitely not a polynomial. It has lots of problems. In general, if you have a rational function, which is in reduced terms, meaning p and q are coprime, or said in other words, they have no common factors, so if you have a polynomial in reduced terms, then the graph will have no jumps, no discontinuities, except at the zeros of the denominator, where the y values of the graph shoot off to plus or minus infinity. And so let's see this. Another thing that you can read off of this is the domain of p over q, p of x over q of x, is all real numbers except for those with q of x equals 0. Right, you can't divide by 0, so you better not wind up with a 0 in the denominator. But that's a polynomial. Let's suppose that that q was like a degree 10 polynomial. What's the greatest number of x values where a degree 10 polynomial might be 0? Sorry, that was maybe not the question I meant to ask. If you have a degree 10 polynomial, how many roots will it have? 10. Well, maybe not all of them, but it'll have at most 10. So, a consequence here is domain has only finitely many holes. And I'll put holes in quotes. There are only finitely many numbers that are not in the domain of a rational function. How many numbers are not in the domain of the square root function? How many negative numbers are there? Not many. So the square root function is definitely not rational. Its domain isn't big enough to be the domain of a rational function. That makes sense? Cool. So let's talk about asymptotes. So as you told me, this thing has some asymptotes. What is an asymptote for a function? An asymptote for a function is some line that function gets really, really close to. Is an asymptote for some curve is a line so that the distance between the line and the curve gets small, as long as you look far enough along on that line. And let's just see, there's the graph of 1 over x. What straight lines does that get close to? You have to say it louder though.
0.
0. 0 is a number, not a line. Sorry, I'm being pedantic.
Y.
Yeah, y equals 0. But yeah, that's absolutely right. It has an asymptote at y equals 0. But if you were to continue graphing this function far enough along, then you wouldn't be able to tell that the graph of the function isn't exactly 0. Is there another line that gets close to? Yeah, which one? X equals 0. And that's why I wanted to be a pedantic talk about what do you mean by 0. because you might have meant two different things, both of which would be correct. But it also looks like it gets very close to the line x equals 0. So what are the asymptotes of this thing? There's one at x equals 0 and one at y equals 0. So there are two that I'll focus on in these lectures. There's another type that you'll have to think about in the course of homework. I won't mention it all in the course of lecture, and that's a slant asymptote. So if a function has an asymptote that's a vertical line, I'll call it a vertical asymptote. So which of those lines is a vertical asymptote for this function? All right, that's a vertical line. It has a horizontal asymptote at the one of those lines that is a horizontal line, namely y equals 0. That makes sense? Cool. So just for the sake of emphasizing, there's a particular thing that I'll want to have happen in the example I'll draw. But take a moment. Sketch a graph that has a horizontal asymptote at y equals 2. So I guess that means it has to get close to this line. And a vertical asymptote at x equals 3. Not drawn to any sort of scale. And a vertical asymptote at x equals -2. And of course there will be infinitely many such graphs. So go ahead and sketch one. Right, I haven't given you enough information to pick a particular graph. And now I think I'll go ahead and ask you guys some questions about the function you just graphed. Does your graph pass the vertical line test? If it doesn't, that's a problem, right? So there's a good sanity check. Maybe I'll draw one also. So here's one. So I need to get close to this line at x equals 2. So maybe it does this and that. And then it has to get close to this vertical line. Let's get close to that vertical line, and maybe it does that. So there's an example of a function that satisfies all of those conditions. Does anyone have any complaints about that particular function? What complaint do you have? Yeah.
It shouldn't be able to touch the horizontal asymptote.
So the definition says of a horizontal asymptote says that for a very big, if you travel very far along the line, the graph and the graph and the line get very close. Horizontal asymptotes don't care what happens for small values of x. You can cross horizontal asymptotes all you want. The reason you can't cross vertical asymptotes is just a vertical line test issue. Yeah, so that's exactly the caution that I wanted to pose. Many rational functions have horizontal asymptotes that they cross. Horizontal asymptotes may be crossed. They don't have to be, right? We saw 1 over x. It has a horizontal asymptote at y equals 0. Does the graph of 1 over x ever cross that horizontal asymptote? It doesn't, so they don't have to cross their horizontal asymptotes, but they can if they want to. So let's just list some quick facts about graphs of rational functions and their asymptotes and intercepts. So if you have a rational function, p of x over q of x, let's go ahead and find its x-intercepts. So what do you need to do to find x-intercepts of a function? see where it touches the x-axis. So you want to plug in 0 for y, I guess. So, yeah, very good. That means you need to like solve p of x over q of x equals 0. Oh, sorry, that's a little bit off the edge. And that thing will go in that space eventually. I just want to walk towards what it is. So if you wanted to like simplify this, we'll be able to solve it all the way. I don't know what p or q are. So, but what's something that you could do to simplify that? What's the only way that a fraction can be 0? Is there any number that I can divide 7 by to get 0? Just say that. Ah, you can't divide by 0 at all.
Oh, yeah, that's like a null solution.
Yeah, that doesn't even exist. You can't. There's nothing you can divide 7 by to get 0. The only way a ratio can be 0 is if the numerator is 0. And if you like, you could see that you could multiply the q of x over to the other side. So I'd give you p of x is equal to 0 times q of x. But that's still 0. If p over q is in reduced form, then p of x over q of x has an x-intercept whenever p of x equals 0. So it's, well, easy to find x-intercepts of a rational function. Just set the numerator equal to 0. That makes sense? If p of x over q of x is in reduced form, then p of x over q of x will have a vertical asymptote whenever q of x equals 0. And let's just see that that like makes sense. So what does it mean to have a vertical asymptote? That means that like on the graph the y values will be getting really, really, really big. And let's see if that actually happens. If I look close to a place where q of x is equal to 0, that means q of x will be basically equal to 0. And p of x will be close to some number. If I take some number like 7 and divide it by something that's really, really, really close to 0, do I get something that's close to infinity? Yeah, 7 divided by like 0.00001 is like 7 million. If I set enough zeros. Yeah, so if you are at a place where q of x is almost 0, then p over q will be almost infinity. It'll be big. So with just those two statements, let's find the x-intercepts and the vertical asymptotes for these functions. And these aren't meant to be difficult. Let's find the x-intercepts. So to find the x-intercepts, I should set the numerator equal to 0. So that means I should set x plus 1 equals 0. What x value will that give me? Good. Where should let's find the vertical asymptotes. That means I should set the denominator equal to 0. So where's the vertical asymptote of this? And maybe just for emphasis, x equals positive 1. That's built into the fact that it's a vertical asymptote. Vertical asymptotes are x. Do you think you can do the same thing for the next two? Yeah. Do it. And remember, since I want to think about graphical stuff, I only want real values. There's a midterm next week, and next week, starting on Tuesday, I'm out of town. So I won't be the one proctoring the midterm. Someone else will be. I will record, and on Monday we'll meet and we'll talk about a set of review problems that I'll post hopefully by the end of today. on Thursday the actual midterm will happen. Cool, so let's say these. X squared minus 1 divided by x squared plus 1. Where are its x-intercepts? Does anyone want me to talk through finding the x-intercepts? Okay, good. Where are the x-intercepts? Yeah. Where are the vertical asymptotes? There are no vertical asymptotes. In some sense, you might say, well, there should be a vertical asymptote of x equal to plus or minus I. But in order to think about that vertical asymptote, you would have to figure out what it means to graph a complex function, which you can make sense of, but we won't in this class. Next one, x squared plus 3 divided by x minus 1. Where are its x-intercepts? Does it have any? Where are its vertical asymptotes? Yeah. Cool. So if you want to do this for an example where everything was more complicated, how do you think you could check all this using a machine? Think we could graph it? I don't think I will, but keep in mind that if you're doing these on homework and you've plotted some properties, you can check by graphing the thing electronically. So let's keep on going. So the next thing I'll do in order to think about how to explicitly graph rational functions, I'll say that, well, especially if you see a linear function divided by a linear function, you can figure out its graph by just thinking about shifts of 1 over x. And in order to do that, let's do some polynomial division to rewrite this. And it'll be some really easy long division. So let's see, I want to divide x minus 1 into x plus 1. And it'll be super easy. What do I need to multiply the leading term of x minus 1 by to get the leading term of x plus 1? 1, right? X times 1 is x. So the first term in the result of division should be 1. Then I'll take 1, I'll multiply it by x minus 1, and I'll subtract. So that'll be minus x minus negative 1 plus plus. We see 2, so there is a remainder of 2. And now I'll say what that means. That means that this rational function is equal to Gesundheit, 1 plus 2 divided by x minus 1. Hey, do you think if we knew the graph of 1 over x, we would be able to graph that? Yeah, I think so. Maybe in order to emphasize it, I'll rewrite it like this. That's 2 times 1 over x minus 1 plus 1. So, flash from the past, but you know what the graph of 1 over x looks like? If you wanted to go from the graph of 1 over x to this polynomial, you would have to deal with the 2, then the minus 1, then the plus 1. So that 2, what would that do? What does multiplying a function by 2 do to its graph? Stretches it vertically or horizontally? Vertically, by a factor of 2. That minus 1 will shift it to the right. Just 1. Yeah, my 1 looks like a 2. That's on D. And then I'll shift it up also by 1 because I think this is also a 1. So, neat. So what'll I do? I'll start with 1 over x, which there's the graph of 1 over x. I'll stretch vertically by 2. So all the y values will become twice as big. But that looks essentially like the same function because my scale was all screwy to begin with. Yeah, that says stretch, but I've misspelled it, right? How do you actually spell stretch?
S-T-R-E-T-C-H.
There's an extra A?
There's no way.
Okay. There. Stretch vertically by a factor of 2, and then go right 1, up 1. And maybe just for emphasis, like I'll just keep track of that vertical and horizontal asymptote. So I had a vertical asymptote at x equals 0 to begin with. I'll shift right. To begin with, I have a vertical and horizontal asymptote at 0. X equals 0 and y equals 0. I shift right by 1. The vertical asymptote will now be x equals 1. The horizontal asymptote will now be y equals 1, because I've shifted up by 1. And then the graph will just come along for the ride. Maybe in order to make sure I have some things correct, how could you figure out, maybe even by using the original formulation, where is the y-intercept of that? How do you find y-intercepts? Plug in x equals 0. What do you get for that when you plug in x equals 0? -1, because I got 1 over -1. So that means it better have a y-intercept there. And otherwise, so I'll have this as my vertical and horizontal asymptote. That makes sense? That seem reasonable? And now let's even just check. So if you, by looking at the graph, where is the vertical asymptote of this polynomial? By looking at the graph of this rational function at x equals 1. By looking at the original formula, where should there be a vertical asymptote? Hopefully it's x equals 1. So the denominator you'll set equal to 0. So it'll be x minus 1 equals 0. Yeah, that's x equals 1. So there is a vertical asymptote at 1. It checks out. That seem reasonable? So the next thing that I want to emphasize is how to find horizontal asymptotes of rational functions. And this will feel a lot like how we determined end behavior of polynomials. So if you have a polynomial and you want its behavior when x is really, really big, when x is at like infinity, you only need to care about the leading term. Same thing with rational functions. And let's just see the statement of it. So if you have a rational function, p of x over q of x, we'll, I think, just do some examples. Imagine the degree of q, the denominator, is larger than the degree of p. So let's just go over here and see an example. So give me an example of a polynomial. X cubed. In order to make it complicated, I'll add some terms. How about x cubed plus x squared plus 1? So let's suppose that that's the numerator. Give me an example of a polynomial that has degree bigger than that. X to the 4th plus 17. And if we want to find horizontal asymptotes, because that's what this is all about, maybe I'll even put some coefficients. 2 in front of the 1 on top, 3 in front of the 1 on the bottom. Sorry, I keep changing it. Makes it hard for you to take notes. Let's try to figure out the horizontal asymptote by thinking about what happens when x is really, really, really big. When x is absolutely gigantic, does the x squared plus 1 make any difference compared to 3x cubed? When x is big, this will basically just be 2x cubed divided by, in the denominator, compared to 3x to the 4th, does that plus 17 make any difference? Let's see, that's 2 over 3x, right? Canceling common factors. Oh, wait, but x is really, really, really big. So if you take 2 in the numerator and divide it by 3 times a really, really big number, what is that close to? It's like 2 divided by 3 billion. That's basically 0, right? That's all the horizontal asymptote is. It's asking what number is the function getting close to when x is really, really big. And whenever you see a rational function, if the degree of the bottom is bigger than the degree of the top, then somehow the thing you're dividing by is getting way bigger than the thing in the numerator. The horizontal asymptote will be at y equals 0. That makes some sense? And there's some intuition there too. But then we just have a statement. If the degree of q is equal to the degree of p, well, let's see an example. 2x cubed plus x squared plus 1 divided by 3x to the 4th plus 17. And let's play the same game again. If I plug in an x value that's really, really, really big, positive or negative, make that 4/3. If I plug in an x value that's really, really, really big, does the x squared plus 1 make any difference in the numerator? Does the 17 make any measurable difference in the denominator? So you'll basically just have 2x cubed divided by 3x cubed. Does anything simplify in that? All the x's do? So this function then has a horizontal asymptote at 2 over 3. And in general, that's true. If you have a rational function where the numerator and denominator have the same degree, then there will be a horizontal asymptote at the leading coefficient of p, the numerator, divided by the leading coefficient of q. That's where the 2 and the 3 came from. That makes sense? And I guess the other case is the case that the denominator wins. So let's see this example. Let's think about 2x to the 4th plus x cubed plus 1 divided by 3x cubed plus 17. And let's play that exact same game. If I plug in an x value that's really, really, really big, only the leading terms will actually make a difference. This will be really close to 2x to the 4th divided by 3x cubed, which I guess that'll be like 2/3 x. But remember, x is really, really, really big. If x is really, really, really big, then what can you tell me about 2/3 times a really big number? It's still big. Multiplied by, not divided by. So it's still big. So it's not getting close to any particular number. There is no horizontal asymptote. Any questions about that? Do the claims seem reasonable? Do they make sense that those things should be true? And I mean, philosophically, if you don't want to remember these 3 cases, you can just think, well, I'm going to see what happens when I plug in an x value that's really, really big. That's big. And that x value will tell you what behavior you expect. So let's check the horizontal asymptotes for these rational functions. So that first function, let's find its horizontal asymptote. The horizontal asymptotes of x to the 4th plus x squared plus 1 divided by x to the 4th plus negative 2x to the 4th plus 2,000 or 20,000, doesn't matter, x cubed. So let's see, what's the degree of the numerator? What's the degree of the denominator? 4. So, of the 3 bullet points in that statement, which bullet point do we land in? The middle one, I guess? So there should be a horizontal asymptote at the ratio of the leading coefficients. So this one should have a horizontal asymptote at y equal to 1 over negative 2. What does that simplify to? Negative a half? Right, negative sign should be in the numerator. That makes sense? That seems reasonable? You guys think you can find the horizontal asymptotes of these remaining functions? Yeah, good. It shouldn't take more than a minute. Cool. Do people want more time before we talk? It wasn't much time, but I don't think it's too much time. Where is the horizontal asymptote? 0. Degree 4 divided by degree 5, that's enough information. You're in the top case, horizontal asymptote is 0. 1. The width degree 5, so there should be a horizontal asymptote of 1 over 1. There is no horizontal asymptote. Maybe I'll go ahead and say we know something a little bit better than there's no horizontal asymptote. Asymptotically, this should look kind of like x squared. So if a really big x value, that'll look like a parabola, which is what we saw over. Nice. So let's close. I'm going to go out of order just a little bit. Instead of thinking about this light application, let's just do a graphing example. And we will come back to this next time. The actual notes content posted for next time takes less than the whole time, so I'm okay going over it. So let's try to use what we've developed to qualitatively sketch a curvature of the graph of that polynomial. X plus 1 times x minus 2 divided by x plus 2 times x minus 1. So, first things first, let's find asymptotes and intercepts. Where are the x-intercepts of that function? Yeah. So in order to find x-intercepts, you would set the numerator equal to 0. And that's really easy. I've already factored it for you. So let's see. There's one at x equals negative 1, one at x equals 2. Where is the y-intercept? How do you find the y-intercept? That's vertical asymptotes. Right, to get the x-intercepts, you just plug in y equals 0. That's not special about rational functions. That's for anything. So if you plug in x equals 0, let's see what we get. I'll get 0 plus 1, that's 1. 0 minus 2, that's negative 2. Divided by 0 plus 2 times 0 minus 1. So that's 1 times negative 2 is negative 2 divided by 2 times negative 1 is negative 2. What's that equal to? 1. Not negative 1. So far, so good. Let's find next the vertical asymptotes. Where are the vertical asymptotes in this function? Negative 2 and 1. Because you set the denominator equal to 0. And that's super easy to do because it's already solved. It's already factored. X equals 1. X equals negative 2. So far, so good? Where is the horizontal asymptote of this function? Yeah.
X equals negative 1, x equals 2.
For the bottom asymptotes? Oh, okay, sorry. I didn't write anything. X equals 1, x equals negative 2. Oh, okay, cool. The horizontal asymptote. What's the degree of the numerator? What's the degree of the denominator? 2. So I'll need the ratio of the leading coefficients. Yeah, if you were to imagine FOILing out the numerator, what would be the leading coefficient? 1? And what is the same with the denominator? So there would be a horizontal asymptote at 1 over 1, which is 1. So there will be a horizontal asymptote at y equals 1. And let's go ahead and notice the y-intercept has the same y value as the horizontal asymptote. So the graph will definitely at least touch its horizontal asymptote. And now let's just do enough to figure out where it should be positive or negative and go from there. So I guess the first thing to check is x values more negative than negative 2. What's an x value more negative than negative 2? No, but what you said is good. Let's plug in a really, really big negative x value. Negative 10 quadrillion. I'm not sure if that's a number. I know where the horizontal asymptote is. It's at 1. So when x is negative 10 quadrillion, the y value should be close to 1. Is the y value close to 1 positive or negative? Positive. And you see, I didn't have to do any computation. I know that it should be positive because it has to be close to this asymptote. It'll get close to that vertical asymptote of x equal to 2. And now, well, now I have to actually do some computation. What's the x value between negative 2 and negative 1? Negative 1.5. Let's plug in negative 1.5. And I realize that I have 1 minute remaining. So I won't be able to finish all of the supporting walk. So I won't try to do the computation. I'll just ask you positive or negative. Is this number positive or negative? Negative? Negative 0.5. Is that number positive or negative? Negative. So the whole numerator is positive. Positive or negative? Positive or negative? So the whole denominator is? So I see a positive divided by a negative is negative. So I know that during this whole stretch it should be negative. I've already evaluated at 0, and I got something positive. And now I don't have enough time to finish the supporting walk. There's qualitative So that was very fast. We'll do another graphing example Wednesday. And we'll also talk through that one very light application.
So excited when you read questions